This is problem 3-53. It's on page, let's see, 154. And I'll read it. Looks like the camera's off just a little bit. There we go, that's better. Okay, so it's on page 154. A piston cylinder device contains 0.005 cubic meters of liquid water at 0.9 cubic meters of water vapor in equilibrium at 600 kilopascals. Heat is transferred at constant pressure until the temperature reaches 200 degrees Celsius. Okay. So let's sketch the system. Here's the piston cylinder device, and we know that heat is going to be transferred into the system. And the volume of the liquid in state 1 was given as 205 cubic meters. The volume of the gas was given as 0.9 cubic meters. So it's not really a surprise that the gas takes up so much more space than the liquid, and yet the bulk of the mass could still be in the liquid. So here's the liquid down there, and of course my drawing's not to scale. Let's see. The pressure is 600 kilopascals. But that pressure would remain constant. If this is state 1, the pressure is going to remain constant because this is a piston cylinder device. In fact, they even make it clear that heat is transferred at constant pressure until the temperature reaches 200 degrees Celsius. So eventually state 2, we know that the temperature in that state will be 200 degrees Celsius. The first thing we're supposed to find is what is the initial temperature of the water. Let's attack that first. Well, if we have water in the liquid and vapor phase in equilibrium with one another, then all we need to do is look up the saturation temperature at 600 kilopascals. When you do that, you'll find that it's 170.43 degrees Celsius. That's table A5 in the back of your book, and that's just the initial temperature. Now, question B says, what's the mass of the water that's in the system? So the total mass of the water. Well, some of the mass is in the liquid phase, some is in the gas phase. We know the volumes of each, but we don't know how much mass is in each of those phases. We can figure it out though, because specific volume is a property of the water, and we can look up the specific volumes just like we can the temperatures. We can look up the specific volume of liquid and the specific volume of vapor at saturation conditions of 600 kilopascals. And once we find them, then we can calculate the mass. And it's pretty easy because you remember, specific volume is just volume per mass. We could rearrange this and say, well then, the amount of mass in a particular phase would be the volume divided by the specific volume. Now notice I use a capital V for total volume and a lowercase v, basically a V with an arm on it, for the specific volume. So for example, the mass in the liquid phase, just this liquid down here, how much mass is there? Well, it's just the volume of the liquid phase divided by the specific volume of saturated liquid at these conditions, 600 kilopascals and 170.43 degrees Celsius. Now, the mass of the gas would be the volume of the gas divided by the specific volume of saturated vapor. If we want the total, well, let me just go ahead and plug in numbers. So the volume of the liquid is 205. Looks like I've got a slightly different problem. I've plugged in 0.1. I don't have a calculator with me, so let me modify this problem just a bit. Instead of working exactly what your author has, I'm going to use a specific volume, a total volume of liquid, initially of 0.1 cubic meters. Now the solution I've got here that I've worked out is from an older version of the textbook, and the numbers have changed just a bit, but the principles are exactly the same. I didn't realize that before I started, so let me just continue, and should come out fine. Anyway, the specific volume of saturated liquid at 600 kilopascals, let me make sure that's still the same. No, this one's for 800 kilopascals, so many of the numbers are changed. So I'm working a problem like 53, but not exactly the same. In fact, the final temperature is 350 in the problem that I'm working. But you can do the same thing, and of course you'll have slightly different numbers. But the principles are still the same. So anyway, the specific volume of saturated liquid at 800 kilopascals instead is 0.001115 cubic meters per kilogram. Notice the cubic meters go away, we'll just be left with kilograms of liquid. Also, by the way, that 170.43 would be the saturation temperature at 800 kilopascals. Okay, for the gas phase, there's 0.9 cubic meters, and it has a specific volume of 0.2404 cubic meters per kilogram. Again, the cubic meters go away. And if we add these two together, we'd have the total mass. So the total mass, when you plug all this in your calculator, is 93.4 kilograms of total mass, and that's the answer to part B. At least for these numbers. You'll have to change the numbers for your actual problem from the 7th edition. Now, the next question, question C, what's the final volume? Well, we've got a problem here. We don't know the phase situation in state 2. We don't know if there's still some liquid water left. There could be. We don't really know. We have to figure that out. Well, if that's the total mass, then we should be able to figure out what's going on in the second phase, or in the second state, excuse me. I'm sorry, I referenced the total mass. I was going to go for volume, but we don't have that. We do have two pieces of information, though, about the second state. Notice that the pressure in state 2 is the same as it was in state 1. And so if you look up 800 kilopascals, 350 degrees, you'll find that that does not exist in the saturation tables, which makes sense. I mean, the temperature has to remain at 170. Since the temperature is above the saturation temperature, then this must be in the superheated region of the water's behavior. In other words, all the water in state 2 is in the superheated phase. It's not even close to saturation. Okay. So, what we have to do is move away from the saturated tables, move into the superheated tables, and look up the properties we need. So we're supposed to find the final volume. Well, if in state 2 we know the pressure and the temperature, then we can look up the specific volume in state 2, right? So you just use the pressure and temperature, go to the superheated tables. When you do that, you'll find that the specific volume is 0.3544 cubic meters per kilogram. Now, since we know that we have a total mass of 93.4 kilograms, all we have to do is multiply this mass by this specific volume, and that'll give us the total volume. So the volume in state 2 is mass times specific volume in state 2. Notice I don't have a subscript of F or G on this specific volume because this is not even close to saturation. So if you multiply 93.4 by 0.3544, you should find the volume in state 2 is 33.1 cubic meters. Now remember, of course, that your numbers will be different because your input problem numbers are slightly different than these. Okay, last question. Draw the PV diagram of this process. Almost out of space, but I think we have enough room to do it. So pressure and specific volume. Well, we want to draw it in relationship to the vapor dome because we know we begin at saturation conditions. In other words, we begin beneath the vapor dome and end up to the right of the vapor dome in the superheated region. The pressure remains constant at 800 kilopascals. So we start somewhere. Well, how much? Well, the amount of mass we had, I didn't calculate the two numbers individually, but I'd be willing to bet that we had a whole lot more mass in the liquid phase. Notice that this is basically 2 orders of magnitude different, whereas these two are on the same order of magnitude. And so again, because of that, I expect the number for the mass of the liquid to be much larger. In other words, the quality is pretty low initially. And so that begins here at a specific volume. Didn't calculate it, looks like. We could get it if we were to take the total volume In fact, we can get this pretty easily because the total volume of the system would be the 0.1 cubic meters plus, oh, I've already done that. It would be the 0.1 cubic meters plus the 0.9, so it's just a cubic meter. So 1 cubic meter divided by 93.4 kilograms would give us the specific volume. Now, I don't have a calculator again, but that's what I should write down here. I'll just write it this way, 1 over 93.4, and the units are cubic meters per kilogram. That's about 1 over 100, so it's about 0.001. It'll be a little bit away from that. Anyway, what does the process do? That's the important question. Well, the pressure remains constant, and we know that we have to move through the saturated vapor region because eventually we get into the superheated region. So we know that at one point all of the water was boiled off and turned into a vapor, but the pressure remains constant even after that. So this is the last point where the temperature would remain at 170.43. The temperature is going to continue up after that, but the pressure remains constant. And we move over here, so from state 1 to state 2, where finally the specific volume in state 2 is this specific volume of 0.3544 cubic meters per kilogram. Notice when your author asks for a PV or a TV diagram, the specific volume that he's asking for, or the volume he's asking for is specific volume, not total volume. That should be assumed. By the way, I actually did perform this calculation. I just looked at my sheet. And it came out to 0.0107 cubic meters per kilogram. Now, for some reason in my diagram here, I've put this point way over here on the right. I don't think that's accurate. I think that the amount of mass in the system that's in the liquid phase is going to be a lot larger, so I think it will actually be over here, closer to the saturated liquid line. So let's see, in fact, we could, because you're going to basically move this decimal place over twice. So this thing is going to have order of 10 or so kilograms, and this one is about 1 over a quarter, and so this is going to have about 4. So there's about 10 kilograms and about 4, which means it's a little more centered than I expected, but this point should be closer to the saturated liquid line.